In this presentation, I'll be explaining DC choppers, also called it is DC to DC converters. Let us see DC choppers. DC choppers means these are DC to DC converters that are used to get variable DC voltage from a fixed DC voltage. From a fixed variable DC, want to get a variable DC output voltage from a fixed DC input voltage. Therefore, that is called a DC chopper or DC to DC converters. And the switching device that are used are self-commutated devices such as power MOSFET, power bipolar junction transistor, IGBT, GTO, etc. is preferred over thyristors for building choppers because they can be commutated by a low power control signal and do not need communication circuit unlike thyristors. Therefore, unlike thyristor, it does not require any commutation circuits, and that is normally for the DC converter or DC choppers, self-commutated devices like power MOSFET, power BJT, IGBT, GTOs are preferred. Now, further, they can be operated at a very high frequency for the same writing. Though, if you are using a self-commutated devices, that can be operated at very high switching frequency. Therefore, the filter size can be reduced. Now, let us see the role of DC converters considering a power system circuit as such. Therefore, here this is a source and this is a load, which is to say load is taken as a motor and motor is coupled to a mechanical load here, and this is called the power modulator. And the power modulator role is if the input is a DC source and the load is either it can be a DC motor or a battery like that one. Therefore, there's a DC to DC conversion is required. Therefore, the power modulator is a DC to DC converter, or we call it as choppers, provided the motor requirement is for the motor DC supply or DC motor, as well as the source is a DC. So this will be converting the chopper. Will be converting the fixed DC into a variable DC that is given to a DC motor. To that one, a mechanical load is being coupled. Therefore, there you requires a chopper. Now, continuing the DC choppers, the circuit that are designed to directly convert a fixed DC voltage into an adjustable DC voltage are called chopper circuits. Already we have seen that one, and it is also known as DC to DC converter or DC choppers. And choppers are considered to be the DC equivalent of AC transformers. And the reason for the same is that similar to the transformers, choppers holds an ability to step up or step down the fixed DC voltage. Like AC transformers, which can be used to either step up or step down the AC voltage, the DC choppers, there are step down chopper or step up choppers are there. The input fixed DC voltage can be either step down or step up by using these choppers. Therefore, that is why we call choppers are to be considered as a DC equivalent to the AC transformers. Now, as a classification of this type of choppers, we have seen that one. This is called AC link chopper. And AC link chopper, actually here, of course, input is a DC and output is again a DC to DC conversion. But in that involves, there are first DC is converted to high frequency AC, like this one, or that is called inversion, or inverter is required to convert a fixed DC into a AC, high frequency AC. Therefore, inverter is required. And after that inversion, that is either step down or step up by using the transformers, then it is being rectified. Therefore, then you will be getting the required DC output voltage. Therefore, that involves that inversion is the either stepping or step down by the transformer is the, then rectification is the three stages are involved in the AC link chopper. But normally DC choppers here, if you have a single switch, which the duty ratio which can be controlled so that the output voltage can be changed. Therefore, there is a input is a fixed voltage, but the DC output voltage can be changed by the duty ratio of the this switch what we are using. Therefore, that in that circuit it is called a chopper circuit or DC chopper circuit, and that involves that is a single stage conversion. Only single stage conversion is required, unlike AC link chopper. DC chopper involves single state conversion and are more efficient also. Therefore, we'll be concentrating this one, DC to DC converter, using a single state conversion. Now let us see the step down chopper. Step down chopper, from the name itself, it is that output voltage is less than the input voltage. That's called step down chopper. It's a DC to DC converter in which output voltage is less than input voltage. And this is the circuit topology. Therefore, this is a self-commutating switching device. chopper switch as either IGBT or MOSFET or bipolar junction transistor. That switch is this one. To that one, here there's a series, there's an inductor is there and the load is there. Therefore, this is totally here the input voltage, the voltage at this point is marked as V0, which is coming across the inductance and the load current is I0, and the voltage is equal to V0. That is across that one, there's a feedback diode, D is connected. Therefore, this is a circuit topology of a step-down chopper. And let us see the working of that one. When the switch is on here, when the switch is on here, we can see that one, the diode is reverse bias because here you're getting a positive voltage. Therefore, the diode is reverse bias. Therefore, that does not conduct. Therefore, this voltage will become same as the input voltage. V0 will be same as the voltage V. Therefore, here, if you see the plotting of that one, output voltage V0 or this voltage V0 will be same as the input voltage V. And during that period, there will be a current, that is the current through the inductor, this one through the and the load. That is, it is building up like that. Why it is building up in a positive direction or a rising direction? Because we are getting a positive voltage across the inductor, because VL equal to L di by dt, or di by dt polarity decides by the polarity of the voltage across the inductor. Since the voltage across the inductor plus here and minus here, when a switch is on here, then L di by dt or di by dt will become positive. That is why the current is slowly building up, which is the same as the load current. And during that period, energy will be stored in the inductor. That is happening during the on period of the switch. So the output voltage equal to same as the input voltage. And when switch is open here, already the energy is stored in the inductor. Therefore, here that will be driving a current with in that case, to drive a current in the same direction, the polarity will become plus here and minus here. Then only it can drive a current in the same direction as per the Lenz's law. It will to drive this one here plus and here minus, meaning that this diode gets forward bias. Therefore, the diode gets forward bias, or that current freewheels to that one. The diode will be conducting, that will be freewheeling through the diode. Then the voltage V0 will become only the diode drop. If you neglect that word diode drop, that will be almost zero here. But during the off period of the switch here, the voltage V0 will become 0, and during the on period of this one, you will be getting a positive voltage V. That will be repeating. Therefore, this is the output voltage or the voltage V0 here, that is plotted here. And this period we call it as on period T on, and this period we call it as off period T off. And the summation of T on and T off, that is called the total time period T, and the frequency is given by, output frequency is given by 1 by T, or which is equal to the F. And that is regarding the output voltage. And if you look into that current through the inductor, when the switch is off here, since the voltage polarity plus here and minus here, we can see that voltage, the VL is now negative, and then we will see that one di by dt will be negative. That is why the current is dropping with a negative slope here. That until the next switching starts, that will be current will be dropping here. Therefore, again, that is current is building up when switch is on here. Therefore, this is the current through the load as well as the current through the inductor, and this is the voltage across, the load as such, including the inductance and the load. So this voltage V0 is shown here. And the average value of the output voltage, that is, this dotted one is the average value of the output voltage, that can be calculated by integrating the output voltage, or meaning that this area is calculated and that is spread over this total time period T. Therefore, that is calculated as average voltage equal to integral 0 to T on V0 dt, then that is divided through the time period T, 1 by T, or we'll be getting T on by T into V, or duty ratio D into V. Therefore, the average output voltage is given by the duty ratio D, which is equal to the on period divided by the total time period. T on divided by T is called the duty ratio. That into the input voltage is the average output voltage. Therefore, the output voltage varies linearly with the duty ratio. Therefore, D into V is the average output voltage, meaning that output voltage is linearly varying with the duty ratio of the chopper. And the output voltage can be controlled in the range, that is, if you change the duty ratio, for example, if you change the duty ratio 0.1, in that case, it is equal to 0.1 times V, output voltage 0.1 times. If it is, you are making say 0.9, it is 0.9 times V. Therefore, by controlling the value, if it is 0.5, the output voltage equal to V by 2. Therefore, by controlling the duty ratio of the switch, you can control the output magnitude of voltage. For average value of the output voltage can be changed, that it is actually more than 0 and less than V. Therefore, that in this limit, you can change by changing the duty ratio D, which is equal to on period divided by time period T. Normally, the time period T will be kept constant, only you will be changing the T on. Or if you make T on equal to 50% of the T, output voltage D equal to 0.5, output voltage equal to half of the input voltage. For this configuration of this chopper is also known as step down chopper. This is we are stepping down the voltage. For example, if you are making this is equal to 100 voltage, and if the duty ratio equal to 50% or 0.5, output voltage, average output voltage equal to 0.5 type into 100, which is equal to 50 volt. Therefore, it is a step down chopper. Therefore, the total time period equal to the sum of the on period plus off period, and duty ratio equal to T on divided by T. Output voltage equal to D times V. It is linearly varying with respect to the duty ratio. Now let us see the second one, step up chopper. In that one, the output voltage will be more than the input voltage, and the circuit topology is like this one. And that is one more thing I want to tell is previously we explained step down chopper that can also be called as certain case it is equal to buck converter. And here this is a step up chopper. Sometimes it is referred as a boost converter. Voltage is increasing. For the step down chopper can be one other name is the it is equal to, but based on the application it can be told as a, and the configuration the topology is same as buck converter, but this is a step up chopper, say boost converter topology, same thing. And here let us see the DC voltage input is there, and here the output voltage V0, the load is connected, and inductor is at the input side, and the switch is across that one is connected, and the diode. So this is the circuit topology of a step up chopper. Now let us see when switch is on. When switch is on here, what is the circuit, equivalent circuit? When switch is on, this is the equivalent circuit, and in that case, here we can see that one, the voltage here when switch is on here, the output voltage, because this voltage output voltage is to become 0, output voltage equal to 0 here. And of course the inductor is in charging, because it will be all the voltage across the inductor is same as the supply voltage Vs. Therefore inductor is getting charged here. That is why the inductor current is linearly changing, and that is changing in this fashion as the chopper is on here. And of course the voltage, since this is on here, the voltage at this point is equal to 0. Therefore the voltage equal to 0 here, and here the voltage is equal to 0, and that is during the on period of the chopper. Therefore equivalent circuit corresponding to on period is this one, and during the on period output voltage V0, that V0 will become 0 because this is on here, this is the equivalent circuit, V0 will become 0. And during that period the inductor, that is this inductor is getting the inductor is in large inductor that is in series with the source voltage, and inductor stores the energy during the on period. During the on period, that is getting charged, and that stores the energy in the inductor. That is happening during the on period of the chopper. Therefore, this is the equivalent circuit when it is switched on, and during that period the voltage, output voltage is equal to 0, and the current is increasing linearly. Now continuing the step up chopper here, during the off period of the chopper switch, and in that case the switch is open here, and already the inductor is already charged there, and in order to drive the same direction the current, that is as per the Lenz's law, in order to drive, as this is switched off, it has to drive a current the same direction. The source, now the voltage across the inductor voltage polarity become plus here and minus here, plus here and minus here, and here we can that will be driving a current through the motor, through the load as such. And this is the equivalent circuit of this, equivalent circuit during the off period. And during the off period, this voltage, that is the voltage across that is the load V0, that is actually, it is the, of course, the sum of this voltage Vs and what is the voltage drop across the inductor, L di by dt. As per the Kirchhoff's current law, if you take that one, this is a potential rise. Of course, here the current is you can minus and plus. Again, it is a rise, and here minus plus rise, and here plus, it's a down. So this voltage is equal to the summation of this voltage Vs plus L di by dt is the output voltage, that is shown here, that is here, this one. During the off period, the voltage across the load V0 is equal to whatever the supply voltage plus L di by dt, that is inductor drop across, that is L di by dt. That because of this is exceeding the source voltage, because we are adding L di by dt towards Vs, therefore that exceeds the source voltage Vs, and the energy stored in the inductor L is released to the load. Therefore, during the switching off the switch, chopper switch, here whatever the energy stored in the inductor is being released to the load. That is what is happening during the off period of the step up chopper. Therefore, this is the equivalent circuit during the off period, and this is the voltage during on period 0. During off period it is equal to Vs plus L di by dt. That will be continuing, and since the voltage is now, the VL is equal to negative here, because plus and minus is taken as positive, here plus and minus, that's why negative voltage. Therefore L di by dt will become negative. That is why current is dropping, the current through the inductor is dropping, like that one. Then again next one, again it is switching on, so that continues that one. Now continuing the step up chopper, and as we have seen, the equivalent circuit during the on period is this one. During the on period, this voltage is equal to 0 because this switch is on, and the energy will be storing the inductor, and the voltage across the inductor is same as, if you write the Kirchhoff's voltage law equation for this loop, this voltage is same as the DC input voltage. It is equal to DC input voltage across the inductor. Since the voltage across the inductor is positive, the current is building up linearly from a certain value, from I1 to I2, it is increasing linearly. And here the output, this is the average output voltage as it is shown here. And here next one, here when switch is off here, the inductor, whatever the energy stored in the inductor will be transferred to this one, and the voltage across the inductor, now it becomes, it is equal to plus here minus here, or this voltage is equal to this plus this equal to this one, or this inductor voltage is equal to V0 minus Vs, or V0 minus Vs is the inductor voltage. Therefore, this is the voltage across the inductor when switch is on, and this is the voltage across the inductor when switch is off. As per the volt-second balance concept as such, the positive area should be equal to negative area. Otherwise, flux will be building up, and that goes into saturation. That is as per the volt-second balance concept. It's like that one. Therefore, normally this area should be same as that. The positive area should be, that is volt in the product of voltage and time. It's called volt-second balance. That is nothing but the flux. Therefore, the positive flux should be same as the negative flux. Therefore, net flux should be, change in net flux should be 0 after one switching period. That is called volt-second balance concept, or that is in order to avoid the saturation of the core. Therefore, let us see the derivation of this step-up chopper in the next slide. Now let us see the step-up chopper derivation of the output voltage. Now the energy input to the inductor during the on period. During the on period, as we have seen, that energy stored in the inductor. That energy stored in the inductor is nothing but what is the voltage across the inductor into the average current through the inductor, that is voltage and current, that will give the power, into the on period T on. Therefore, that is give the energy. Therefore, the energy stored in the inductor during the on period of the switch is given by what is the voltage across the inductor into the average current through the inductor, voltage into current, that's give power, into the on period. The voltage across the inductor during that period is equal to nothing but the input voltage Vs. And the average current is equal to, this is I1 and this is I2. Average of this current is given by I1 plus I2 divided by 2. I1 plus I2 divided by 2. And the time, this is equal to the on period T out. Therefore, this much is the energy stored in the inductor when the chopper switch is on. Similarly, this energy is being released to the load during the off period. Therefore, energy released by the inductor during the off period is given by what is the voltage across the inductor into the what is the average current through the inductor during the off period and into T off. Therefore, voltage across the inductor during the off period is given by, it is equal to V0 minus Vs. V0 minus Vs. And again, the average current is given by I1 plus I2 divided by 2. And that into the off period. That is off period. Therefore, this much energy is released from the inductor into the load. Therefore, if considering the system is to be lossless, equation 1 should be same as the equations 2. Or equating 1 and 2 here. If you equate 1 and equation here, then we can see that one Vs into I1 plus I2 divided by 2 into T on equal to V0 minus Vs into I1 plus I2 divided by 2 into T off. This will be cancelling. Or here now equation Vs into T on equal to V0 minus Vs into T off. Or that indicates that Vs into T on plus T off equal to V0 into T off. V0 into T off. Or we can see that one V0 into T off. Or V0 equal to Vs into T on plus Tf divided by T off. or it is equal to, dividing this one, it is equal to Vs into, this is equal to T by T of, which is equal to Vs into T by, T of can be written as T minus T on, T minus T on. Now dividing T numerator and denominator, Vs into 1 by 1 minus T on by T, which is equal to duty ratio. Or the average output voltage V0 equal to the input voltage Vs divided by 1 minus D. Therefore, that equation is that one, V0 equal to Vs divided by 1 minus D, where D is the duty ratio, which is equal to T on divided by total time period T. Duty ratio equal to T on divided by T. And as an example here, if duty ratio, if you select D equal to 0.5, V0 will become Vs divided by 1 minus 0.5, it is equal to 2 times Vs. Therefore, if you take the input voltage as say 50 volt, and if you make the duty ratio as 0.5, output voltage equal to 2 times 50 or 100 volt. Therefore, that is why it is called a step up chopper. Output voltage will be more than the input voltage, and that can be varied by using the duty ratio. The relation is that output voltage equal to the input voltage, source voltage Vs divided by 1 minus D, where D equal to T on divided by Tf. Therefore, that this is the voltage across the inductor during on period and off period. This is the current through the inductor. And similarly, here the output voltage, when output, this is average output voltage is average of this one, and that is marked as, this is average output voltage, and this is during on period 0, during off period it is equal to VL plus LDI by dt, and average output voltage shown is here, which is equal to V0. Therefore, this is the average output voltage, which is equal to V divided by Vs divided by 1 minus D. And this is the load current. This is the load current, the current through the load as such. Continuing the step-up chopper, the principle of step-up chopper can be employed for the regenerative braking of the DC motor. It can be used for regenerative, but that concept can be used. Therefore, in that case, we are changing. This is the chopper circuit, but we already discussed here. Now, in this case, the Vs represent, if you represent Vs as the motor armature voltage or the motor as such, and V0 is the DC source. If you replace this one as the DC source, and if this is the motor here, then the energy will be drawing from the motor into the source, or that is working as, that's called the energy will be feeding back from the motor into the source, or it's called regeneration we call, or we can say that one, the mechanical energy will be converted into electric energy, or that is actually operating in the second quadrant we call it as. Therefore, that the same circuit is shown here. Here the same as in that, only thing is that here this is the motor load, RLE load, it's a DC motor, and this is a battery source. And in that case, if you are making the duty ratio, I mean, by controlling the duty ratio, we can, feedback for this energy. If this voltage is to be more than this one, so that the diode will be conducting and the current direction will be reverse. Of course, the voltage polarity will be there, but the current is the reverse, and therefore we can see that one. Of course, the power output is negative, or we can say that one, the power is flowing from this one, that is from this motor source into the DC source. Therefore, that in that case here a reverse torque will be produced, and that's called the braking action is in place. Therefore, that's called the regenerative braking, because the current polarity is now reverse, and that will be produced in a reverse torque, and that will be braking the motor. That is why it's called the regenerative braking, in which the power is flowing from, or the motor into the DC source. Therefore, that is happening when by using a step-up chopper, that can be realized. The principle of step-up chopper can be employed for the regenerative braking of the DC source. Therefore, that is shown here. Now, let us see another topology which is called step-down and step-up chopper. For that, circuit topology can either step-up or step-down. Both can be done by using that circuit. And for the circuit, the step-up as well as step-down chopper provides an output voltage that can either it can higher or lower than the input voltage. That is called step-up or step-down chopper, step-down and step-up chopper. And assumption is that load voltage is constant. V0 is constant because large value of the capacitor, of course, large value of capacitor is used. Therefore, the load, what we are assuming is that load voltage equal to constant by using a large value of capacitance. Therefore, this is the circuit diagram of a step-up, step-down chopper as such. And here the switch is, the chopper switch is that. And here the inductor is the, and now the diode direction is in now direction, and this is the load. And of course, to make the constant output voltage, and we are connecting a capacitor also. For this is a circuit topology of a step-up, step-down chopper as such. And now let us see the working when the two cases, when switch is on, what is the equivalent circuit, and let's see that what is the voltage across the inductor. And similarly, when switch is off, what is the equivalent circuit and what is the voltage across the inductor. Now, first we can see that when switch is on here, that is when switch is on here, this is the circuit there. In that case, the diode is getting reverse bias because we are getting a positive voltage, diode is getting reverse bias. Therefore, the circuit is like this one. This is a broken, it's broken here. Therefore, this is the, or in that case, the total input voltage is coming across the inductor, and the voltage across the inductor is same as the input voltage V here. Therefore, that is the equivalent circuit when chopper switch is on here. And similarly, and the corresponding voltage equal to VL equal to V. And when switch is off here, and during this period, energy will be stored in the inductor. And when switch is off here, whatever the energy stored in the inductor, that will be driving a current through that one. Therefore, in that case, here you'll be getting an output voltage. But here the voltage across the inductor, here the polarity, it has to drive a current. Therefore, it will be the voltage polarity will become VL plus V0 will become 0. Here it is here. There will be a current in this direction because diode is conducting. The current direction is like this one. Therefore, here plus polarity and here minus polarity. And therefore, this will be driving a current in the same direction, here plus and minus. Now, if you write the Kirchhoff's voltage law equation here, this one plus this one is equal to 0, or the voltage across the inductor is equal to minus times V0. For V0 is taken as this one, which is equal to here plus here and minus here. VL equal to minus V0. For this is the equivalent circuit of the step down, step up chopper, step up, step down chopper when the switch is off, and this is the equivalent circuit when switch is on. When switch is on, the voltage across the inductor equal to V, and when switch is off, the voltage across the inductor equal to minus V0, where V0 is the average output voltage, constant output voltage. Now let us derive the equation, that is the relation between output voltage and input voltage conversion equation. In that case, during T-on, as we have seen, that is the during T-on period, the voltage across the inductor equal to V, and which is equal to voltage across the inductor, which is equal to L di by dt. And in that case, we can say the voltage across the inductor equal to V. And in that case, current is building up from a certain value from I1 to I2, the current is increasing. Or the L di by dt, the change in current is given by I2 minus I1 divided by whatever the duration is equal to the on period T-on. Or it is equal to L divided by the change in current I am representing as delta I divided by T-on. Therefore, this is the voltage across the inductor, VL equal to L di by dt during the on period. Or from this equation, we can say that the change in current delta I is equal to, which is equal to voltage V, that is the input voltage V, which is equal to VL equal to V. Therefore, in terms of that V into T-on divided by L. Therefore, this is the voltage, the delta I, that is I2 minus I1, that is equal to V into T-on divided by L during the on period. And during the off period, as we have seen, it is equal to the inductor is this is off here, and the energy stored in the inductor will be driving a current through that one, and the voltage across the inductor is given by this is the voltage, minus V0 is the voltage across the inductor. Therefore, here VL plus V0 equal to, or output voltage equal to minus VL equal to minus V0, V0 equal to minus VL. Or here V0 equal to minus VL, or it is equal to minus of L into I1 minus I2 divided by T off, because it is changing from this one. Therefore, I1 minus I2, that period equal to T off, which is equal to minus L I1 minus I2 divided by T off, or minus L into minus of I2 minus I1 divided by T off, or I2 minus I1 is taken as delta I. Therefore, this minus and minus cancels, or L into delta I by T off. Therefore, that is the voltage, output voltage during the off period, which is equal to delta I divided by T off. Or delta I can be written as the delta I equal to V0 into T off divided by L. That's the second equation. That is during the off period. Therefore, the during on period, delta I can be written as V into T on divided by L, equation 1. During the off period, delta I, the change in current can be written as V0 into T off divided by L. Therefore, equating this equation 1 and 2, because are delta I, we can get it as equal to V into T on divided by L equal to V0 into T off divided by L, or V into T on equal to V0 into TF, or we can get it as V0 equal to V into T on divided by T off, or again T on TF equal to T minus T on divided by T minus T on, or into V, or V0 equal to, again dividing by T here, D by, again T means 1 minus T1 by T, which is D, or D by 1 minus D into V, or V0 equal to D by 1 minus D times V. This is the equation, or relation for the output voltage and input voltage. V0 output voltage equal to D minus 1 minus D times V. Therefore, in this case, if D is less than 0.5, we can see that if less than 0.5, the voltage is stepping down, and if D is more than 0.5, the voltage is stepping up. Therefore, by controlling the value of the duty ratio, we can either you can step up or step down the output voltage. Therefore, that is called the step down and step up chopper. Now, continuing the step down, step up chopper. In that case, the relation between the average output voltage and the input voltage V0 and V0 equal to D by 1 minus D times V. Therefore, by controlling the D, you can vary the average output voltage. For example, if you are keeping the D less than 0.5, we can see that output voltage will be less than the input voltage. That is called a step down operation. For example, if D is equal to say 0.2. 0.2 means it is equal to 0.2 divided by 1 minus 0.2 times V, or 0.2 divided by 0.8, or 2 by 8, or 1 by 4 times V, or 0.25 V. Or you can step down the voltage by making the duty ratio less than 0.5. That is called a step down operation. Now, if you make the duty ratio more than 0.5, duty ratio nothing but T on divided by T. If you make it is more than 0.5, the output voltage will be more than input voltage. For example, here again, if you see that one, if you make the duty ratio say 0.8 here, it will become 0.8 divided by 0.8 divided by 1 minus 0.8, or 0.8 divided by 0.2. 0.8 divided by 0.2 means 8 by 2, or 8 by 2 means it is equal to 4 times V. Therefore, the output voltage will be more than the input voltage. Therefore, if you make the duty ratio more than 0.5, the output voltage will be more than the input voltage. And if you make the duty ratio less than 0.5, the output voltage will be less than the input voltage. Therefore, this circuit can be operated to make either the voltage increase more than input voltage or less than input voltage. That is why it is called step up, step down, chopper. Step up, down, chopper, or either can be step up or step down voltage. Therefore, that is the concept of step up and step down chopper.